Welcome. Today we're going to start our conversation on chapter 12 and through 14. We're going to be talking about bonding, all different types of bonding. There are three major types of bonding, but we're actually mostly going to look at two. So let's consider two different types of chemical bonds. These are things that we've talked about in the past. We have ionic bonds, and we in the past referred to it as molecular bonds, but we're going to try and kind of readjust our term. Instead of calling it molecular, we're going to start calling it covalent. I understand that covalent is the same thing as molecular, but we want to kind of adopt a new term. Instead of calling it molecular bonding, we're going to start calling it covalent bonding. Now, bonds form in elements in order to form a sort of stability amongst those elements. So we have potential energy in each element, and they form those bonds in order to reduce potential energy. And when they do that, they make themselves more stable. So bonding is a pursuit of stability. That's why they bond. Let's keep going. Now, we have a lot of different things that we're going to talk about here. Let's give ourselves like a little bit of an overview. So we're going to be talking about orbital diagrams. So our orbital configurations are going to be really important here. We're going to be talking about what are called Lewis structures, which are like visual interpretations of molecules and polyatomic ions in somewhat of a 3D space, like how those things bond together. We're going to be talking about what's called molecular geometry, again, like the way that those things are oriented in a three-dimensional space, what those molecules actually look like. Along with molecular geometry, we're going to be talking about something called hybridization, which is the concept of like how do these things fit together in the space and how does it really make sense? Where hybridization is the answer for that. We're going to be talking about polarity, which is like the difference in electronegativity between molecules. We're going to be talking about bond polarity. I kind of did these in the wrong order, but there's two different types of polarity. There's polarity in between a bond, and there's polarity of the overall molecule. And then we're also going to be talking about what's called intermolecular forces. So every molecule has independent forces that are acting on that molecule. We're going to be talking about all of these things in this chapter. That's why it's 3 chapters. Let's get right into it. So let's first talk about what I would say is the more simple type of bonding. We have ionic bonding. Ionic bonding occurs between a metal and a nonmetal. It's a little bit more specific actually to talk about it as it's something that occurs between something with a really high electronegativity as compared to something with a really low electronegativity. Luckily for us, the trend exists on the table, which makes the first definition true as well. A lot of the metals are here on the left side of the table, and most of the metals have a really low electronegativity. A lot of the non-metals are here on the right side of the table, and they have a really high electronegativity. So that trend does hold, but metal and non-metal is often a safe way to think about it. Now, this involves a transfer of electrons. It's really important to remember this term here. Transfer of electrons means it's complete transfer. Now, we have sizes with our ionic compounds. We've kind of talked about this a little bit before. Atoms that tend to gain electrons become larger, so that means anions. They become larger than they used to be. And atoms that tend to lose electrons become smaller. Okay? So this is something that we've seen before, like say, for example, I was trying to compare the size between sodium and sodium ion. Sodium ion loses that electron. It takes away, in fact, an entire orbital layer, an entire energy level, so it gets much smaller. Whereas opposed to chlorine and chlorine minus, Cl minus, chloride, right? Those things, the chloride is much larger than chlorine because it gains an electron, which expands that outside orbital. These are the things that we were talking about in our previous chapter. Whenever we look at these ions that are forming together, they form what are called crystal lattices. And crystal lattice structures, to give you kind of a general idea, the way that they look is something like this. I'm going to pause and then I'll come back. This isn't anything that I expect you to draw, but I wanted to take a second and at least illustrate this for you. So as you can see, when we have these big positive and big negative charges, we create this thing that's called a crystal lattice, where kind of like a checkerboard, we alternate. Positive, negative, positive, negative, positive, negative, both up and down. These are called crystal lattice structures. So when ionic compounds do this, they're really strong because everything around that particular ion is strong attraction. So these are really strong, but it also makes them quite brittle, which is why if we take an ionic compound and whack it, it often breaks, it shatters, because as soon as it gets like this, right, say for example, if you whacked it, as soon as it gets like this, we now have repulsive forces and it breaks off. So this is an explanation as to why ionic compounds are often considered brittle is the best word. So, but this is what a crystal lattice structure looks like. Something to keep in mind. So we can draw what are called Lewis structures for ionic compounds. And a Lewis structure just means that we want to look at the Lewis dot structure between two different things, and we want to see if we can explain why the bonds are forming the way they're forming. So let's look at the Lewis dot structure between sodium and chlorine. We're going to start by drawing the Lewis dot structure. So sodium has 1 valence electron, it's in group 1, and chlorine has 7. I'm going to draw chlorine's dots in a different color. Let's draw chlorine's dots in yellow. So that's chlorine's dots. And what's happening here is that sodium is ready to donate a proton where chlorine is ready to accept. Sometimes a really great analogy to think about this is like tug of war. You know, any sort of electron sharing is like a game of tug of war. In this situation with ionic compounds, imagine that on one side of the rope you have like, I don't know, like 8-year-olds, right? Like 8-year-olds, 7-year-olds, you know, little kids are on one side of the rope. And on the other side of the rope is like 17 and 18-year-olds. So, you know, like teenagers, like much older people. If they're playing tug of war, the 18 and 17-year-olds are going to completely take the rope from the kids, right? Like that's probably a no-brainer. And that's what's going to happen here, is that we are going to have a complete electron transfer. We denote this with these kind of curly arrows. We have a complete electron transfer between sodium and chlorine. And the thing that we have that's new is we have sodium as an ion. Draw my bracket a little too big there. And we also have chlorine as an ion, but chlorine has dots around it now. It also has sodium's dot because it has taken complete possession of that dot. And now we have the two sitting together. And that's, now that they're both attracted to each other, they stick together. Chlorine gets to keep all the electrons. It's happy. Sodium doesn't have those extra electrons on the outside. It's happy. Everyone's happy. And they're fine with this. This is how they form those bonds. So that's what this looks like. Let's try one that's a little more complicated. Let's look at something like magnesium and fluorine. I want you to try this one out for yourself for a second. Like pause for a moment and run through it and see how it goes. Okay? Now maybe when you were doing it, you got something like this. If that's the case, then you might realize that there's something wrong here, right? Magnesium has that 1 electron left over, and that's not really good enough for magnesium. So what does it need to do? Well, if you think about the way that this works like in an actual lab environment, we don't just have 1 atom of magnesium sitting around. Say, for example, we had a piece of magnesium and we were passing it through fluorine gas. We don't just have 1 piece of magnesium, like 1 atom, and we don't just have 1 atom of fluorine, right? We have practically infinitely number of magnesiums and infinitely numbered fluorines. So instead what's going to happen is that we are going to have an additional fluorine here that is going to assist in taking that electron. So then instead of this, I'm just going to kind of scoot this over, we are going to have a magnesium that has no electrons on it. It forms a +2 charge, and we now have a fluorine on both sides. And these fluorines both have 1 of magnesium's electrons. And all this really does is kind of explain why we are finding the ratios that we're finding. If I were to write this as a formula, I would write this as MgF2. And I would write this as NaCl, which are the ratios that we were finding before when we didn't really know any better, right? We were doing, you know, a 2-to-1 or a 1-to-2 or anything like that. These are the explanations as to why. This is why those ratios exist, is because it takes that many fluorines to take all of those electrons off of the magnesium. Okay? So this is happening because all atoms, most, not all of them, are trying to become like noble gases. We've kind of talked about this a lot. When we were learning about our charges, we always said everything wants to dress like a noble gas. So everybody's trying to look like the noble gases. Now, polyatomic ions are groups that often behave as single ions, and we've talked about the polyatomic ions a lot. I'm going to take a second, I'm going to rewrite the polyatomic ions. You do the same because you're going to have to memorize them again, so please don't forget your polyatomics. I don't think you have, but in case you haven't, here are the polyatomics. Here are our polyatomics. Again, I don't really have any sort of doubt that you have kept these in your mind, but in case you need to refresh yourself, I would just write them back in so you can remember that you need to know these polyatomics because they behave somewhat differently than other things. Now, we also want to talk about the other type of bonding. It's actually the type of bonding that we're going to spend most of our time talking about in this particular unit. We want to talk about covalent bonding, which again, we oftentimes refer to sometimes as molecular bonding. That's what we called it in the past. Now, molecular bonding in the past we referred to as a nonmetal and a nonmetal. In other words, two things that had a low ionization energy, or excuse me, both things that had a high ionization energy bound together. That's what molecular bonding is. But now let us take some time and let's practice using the new term. So we're going to start calling this covalent. The difference between covalent and ionic is that covalent is sharing of one pair, one or more, I should say. You should probably add that in. One or more pairs of electrons. Now, these bonds, again, are forming to lower potential energy and to make things more stable. When they have a roughly the same level of electronegativity, they decide to share instead of having nothing at all. So again, if we go back to our tug of war analogy, instead of having children on one side of the rope and big teenagers on the other side of the rope, this is a situation now where we have a tug of war game that's evenly matched, and they're both pulling with each other, and they both get to hold onto the rope. So in this analogy, they are sharing the rope. They are not completely dominating the rope. Now, the way that we can show this is through orbital diagrams in a lot of ways. But before we do that, let's just take a second and let's practice with just our Lewis structures like we saw before. Say, for example, I had chlorine and chlorine. I don't know why I wrote the line like that. Let's just say we have chlorine with chlorine, right? Let's do the dot structures for both. I'm going to do these dots this color and then these dots yellow again. Now, in this situation, chlorine and chlorine have very similar ionization energies. Their electronegativity is pretty much equal. So this chlorine is going to say, hey, you know what? Give me that electron. And that chlorine says, haha, nice try. You give me your electron. And then they are kind of both pulling at each other's electrons. And they say, you know what? You know what's better? Let's just share. It's better to share than to have nothing at all. So they're going to decide to share. So our new structure looks something like this, where we have both chlorines that are somewhat stacked on each other, but we have this place here, right here, where they are bonded together. Their electrons are sharing. That's like the share zone. They are bonded together in that point. And that is what a covalent bond looks like. But again, we can also analyze this through the lens of orbital diagrams. Like, let's say, for example, that we look at the orbital diagram of F2. Let's write the electron configuration for fluorine and also for fluorine. Why don't you pause and do that? Like, write the electron configuration for fluorine, and then we'll explore together. Something like this, right? So, remember that they're going to share unpaired electrons. So the sharing is happening here, which means that our Lewis structure for fluorine and fluorine is going to be very similar to chlorine and chlorine. Well, let's say something a little more interesting. Let's look at something like O2. So again, take a second, pause, and draw out the Lewis, or not Lewis, excuse me, the orbitals for O2. I'll give you a second to try it out. So in this situation, we have two free sets of electrons. These here and these here, and those there and those there. So if I were to draw my dots this time, I'm going to draw them like this. If I were to put these two things together, notice that I would bind together two different sets of dots. So I would have one set of dots that are shared, and I would have another set of dots that are shared. And this is how the oxygens would behave around each other. And this is what we call a double bond, something that we'll talk about in a little more detail later. Notice that there are 4 electrons involved. Oxygen double bonds with itself. Now let's look at one more example. Let's look at something like H2O. Good old-fashioned water. Take a second, write out the electron configuration for H. Ooh, where are you going? Sorry, my screen ran away from me. Write out the electron configuration for H. Write out the electron configuration for oxygen. And write out the electron configuration for H. Do it in this order, then you can really see it. See you in a second. So in this situation, you might be able to see that oxygen is going to have all of these different electrons around it, but it still has 2 electrons that are by itself. That's what the orbitals tell us. The hydrogens, however, each only have 1 electron to their names. So when they bind together here. That's where the sharing happens. So hydrogen's going to give its electron to oxygen, and instead of completely dominating that electron, they just share. And we get a structure that looks something like that. We have the oxygen in the middle, and we have the 2 hydrogens on the outside. And we'll talk a little bit more about why oxygen is in the middle specifically as we continue on. This is the end of this video. I don't want to really talk anymore after this. And that's it. So that's bonding. So again, ionic bonding is a complete transfer of electrons, whereas covalent bonding is sharing. That's really the important thing to walk away with here. And the sharing is happening, as you can see in the covalent bonding, it's happening in the place where we have lone pairs or unpaired electrons. Those unpaired electrons, I didn't mean to say lone pairs, I meant to say unpaired. Those unpaired electrons are the places that bonding is occurring. And we'll explore that more next time we start talking about Lewis structure for molecules. See you there.